Okay, next presentation is from Tommaso Zanella from Cineca, who is working one on development inside the HexaFOAM, is a YoctoFOAM minimal C++ re-implementation of OpenFOAM for testing the potential performance gains of GPU porting. The work that will be done together with Simone Bednar, and I would like also to mention the former developer Mirko Valentini, who started the work. Yeah.
Good morning, everyone. So let's move on, since we already had a mention of HexaFOAM. HexaFOAM aims at improving the performances of OpenFOAM on HPC infrastructure. Here is where we are at for HPC. One thing that, okay, I highlighted our entry into the list, Leonardo, although we are still tuning it up, so the results I will be presenting were not run on Leonardo. Now, what we can see from this top 10 updated to June of this year is that 7 out of 10 use GPU technology. So GPU technology is becoming, I mean, a sort of unavoidable aspect of HPC nowadays. GPUs work a bit differently than traditional CPUs. They have a lot of small, let's say, computing units that run in parallel. And in order to best take advantage of all of this massive parallelism, we have to keep as many of these small computational units as busy as possible for as long as possible, which usually means to feed them data to work on as quickly as possible. This means that it's not trivial how to translate an algorithm to work to fully exploit the potentials of a GPU. And often when we are working with existing codes, like for example, OpenFOAM, the question that arises sometimes is whether we should just port the code as it is, or whether we should start to rethink some of the core structures of or core assumptions of the code in order to better take advantage of this architecture. Now, porting OpenFOAM onto GPU is nothing new. There have been many developments. There are currently many developments. Some like rapid CFDs are fully ported. They fully ported some of the solvers of OpenFOAM already, I think, about 8 years ago. Although it's a third-party branch, let's say, third-party fork. And another approach, which we have seen a lot of examples in this workshop, is to take a piece of OpenFOAM, port that to GPU, and study the performance benefits of porting it to GPU. One popular target, for example, is the solution of the linear system, as we just saw. Another popular target is the gradient computation that makes for a very good proof of concept. If anybody saw Giulio Malenza's presentation yesterday. What we did at Cineca is something a bit different. We considered that working on OpenFOAM directly would have been a bit too work intensive. So in order to have a freer hand to explore possible avenues to improve performance and to choose what might benefit from changes and to make a GPU port, we implemented our little toy code. We called it YoctoFOAM. If you're curious, there is a link to our GitLab repository, which is written in C++. It is representative, let's say, of some aspects of OpenFOAM, in particular the core data structure and the core numerics. It is structured in mainly 4 libraries. 2 are related to I/O and they are not of interest for us right now. The core library is the one that approximates, let's say, the high-level aspects of OpenFOAM, so defining the numerical scheme on a high level. And the numerics library is the one that contains all the basic algebra, and it contains it in the form of pure C functions. We call them kernels. Here is a full list of all the kernels that we use to run our version of SimpleFOAM. seem like complicated names. Instead, they just represent some basic stuff. For example, A, X, P, Y operations between vectors and stuff like that. And this modularity allows for us, for example, to take in block this numerics library and substitute it for one that is tailored to running on GPU. So we recreated two of the solvers of OpenFOAM, SimpleFOAM and IcoFOAM. We will focusing on SimpleFOAM. Here is basically the same passages that it follows on OpenFOAM as well. And for the solution of the linear system, we use the per-conditioned conjugate gradient. Here's the same passages as the implementation in OpenFOAM. As a per-conditioner, we are using a very simple diagonal Jacobi per-conditioner. What YoctoFOAM is not a replacement for OpenFOAM, of course. It has many limits. It has a less than a fraction of all the options and functionalities of OpenFOAM. We only ported recreated two solvers. You cannot run turbulent cases. Everything is laminar, and you cannot do domain decomposition. This will be relevant later on. Now, in order to do a porting of YoctoFOAM onto GPU and see what are the potential performance benefits of a similar port in OpenFOAM, we used OpenACC. OpenACC is not a language in itself. It's API that provides some so-called pragmas. They are compiler directives that tell the compiler how to run in parallel on a GPU code and how to handle data movement. Data movement is quite important because in our current state, the GPU has its own physical memory. Unified memory so far at a hardware level is being worked on, but not available in current state-of-the-art HPC machines. So we need to keep track of whether our GPU has already all the data that it needs to work on. In YoctoFOAM, what we did, we simply created copies of all the data structures in the core library to the GPU. And once they are there, they can just be left there, live there, and be operated on there without any exchange between the main memory and the GPU memory, except for a few values like residuals in order to do flow control, decide when to interrupt iterations, etc. So here is an example of what we call a kernel. So these C functions that represent the numerics of OpenFOAM inside YoctoFOAM. They all have this big interface, which is just a few parameters. The parameters are a few and pointers to the data that it needs to operate on. Here is an example of how OpenACC looks. These are the pragmas. These pragmas in particular tell the compiler that all of this data is already available on the GPU because we already made this copy at the beginning. And this pragma here instead tells us, okay, everything that is in this block right now it's not collapsed, will be executed on the GPU. So what is inside this block? This is basically what OpenFOAM does to compute the gradient, although OpenFOAM does it in two different places. We have a first step interpolating at the cell faces the values of our variable, and then a second part that distributes to the neighboring cells the contribution to the gradient. This part is really easy to run in parallel. We just add this pragma here that says, okay, spread this over all the threads of the GPU, just assign a face and run it this way. This other part is a bit more complicated for one reason. Basically, we are still sending each face to different threads of the GPU, but there is a possibility that two faces at the same time may try to write their contribution to the same cell. This is called a race condition. It's something that we don't want to happen because it can create unpredictable behavior. This approach here is the simplest possible way to avoid it, which is adding these explicit atomic clauses that tell the compiler avoid it. They are usually considered not particularly efficient because they add some overhead because the compiler has to keep in check that this doesn't happen. Usually what is preferred to do, well, when we encounter a situation like this, when we feel like we need to use atomics, this is where we should start to rethink our code. This is where we should think, okay, how can we do it differently so that we wouldn't need to use atomics? Which is what Giulio Malenza, if anybody followed this presentation, did exactly for the gradient computation. By changing this loop and looping over cells instead of faces, and then doing inside the loop over cells, a loop over the faces of those cells done serially. And in this way, possible conflicts like race conditions were avoided. We tried to implement the same strategy in YoctoFOAM, but we did not find any advantage. In fact, we found that that particular strategy runs a bit slower for us, at least. That's not, I mean, the behavior of atomics is a bit tricky because it depends a lot on the vendor. NVIDIA apparently invested a lot in making them as efficient as possible. So sometimes they outperform their absence, which is the correct way to do things. And evidently, this is one of those cases, but that may not be true on another machine or using a different compiler or using a different approach than OpenACC. So this is what works for us, let's say, without having to alter the code. To obtain some results, we used a very simple test case. It's a three-dimensional lid-driven cavity, basically a cube with a sliding face on top, very low viscosity, so that it's laminar, 25 iterations of simple, and our preconditioned conjugate gradient. We generated the meshes with block mesh. We have 4 meshes that we're testing of different sizes. The biggest one is 20 million cells, which is as much as we can fill in one Volta GPU of Marconi 100, which is the cluster that we used for the tests. And here are some results to samples of what the solver actually prints out, which is supposed to resemble what OpenFOAM prints out. These are the results, the average times for simple iterations on CPU and GPU, and the speedup. The speedup grows with the size of the mesh. For the smallest mesh, which is about 8,000 cells, the CPU is actually faster because we are not giving the GPU enough work, let's say. And then as the size of the mesh grows, we reach a sort of asymptotic value of about 45. This might sound impressive, but it really isn't, because there is a caveat, a big caveat. As I said, YoctoFOAM cannot run with domain decomposition. So we are comparing a GPU, which is inherently parallel, with a serial run on one power 9 core of Marconi 100. Usually the comparison that they tell people to do is between one GPU and one entire node. One entire node of Marconi 100 is 32 cores. So let's pretend that we did domain decomposition and that it's scaled perfectly. In that case, we would have a speed up of about 32 for the CPU times, and we can do 45 divided by 32. Turns out that the speed up of the GPU is closer to 1.4. which is nothing to write home about. So this is essentially what we can obtain with this particular approach. So using OpenACC, which is not CUDA, without really changing any parts of the code. The code is essentially as it was implemented by my former colleague Mirko Valentini to resemble as much as possible OpenFOAM, save for a few differences. These are some of what we call kernels, those C functions that handle the more low-level numerical aspects, and how much time they take in microseconds, how much times they were called. The ones that were called the most, the first 9, are the ones that are needed for the preconditioned conjugate gradient, of course. And we see that in the 10th place, even if it's called only 50 times, so 2 per simple iteration, the gradient computation is actually one of the more expensive if we consider time spent per call. And the other one, in terms of time spent per call, is the off-diagonal part of the vector matrix vector multiplication, These are two instances in which we have similar loops to the one that I showed before, in which we need to use atomics if we don't want to alter the code and use, for example, a CSR format, and in which we suffer a bit the fact that the neighbor list of cells is not in order, and so there are jumps in the memory, and it's really difficult for to have a good cache performance. So that was all.
Thanks, Tommaso, for the very nice job. Just, I was thinking that could be, I don't know if you are thinking or is in planning in HexaFOAM to try some solvers that are more suitable for GPU. Try to replicate this for some multi-grid, maybe. I don't know, algebraic or geometrical. Could be a big effort.
Yeah, that's definitely an idea. I mean, it depends what you want to do. If you want to do something that performs good, definitely. If you want to do some proof of concept, usually the simpler the linear system is, the better it scales. So I think that for this first show and tell, let's say, phase of the project, probably the conjugate gradient was the best option. Yeah. After that, I think that one thing that Simone has in mind was to use parts of what he already worked on with PETSI4FOAM and try to take some of the things that we developed inside YoctoFOAM to port even more of OpenFOAM onto GPU and start to merge the two approaches. And yeah, that's a thing.
Okay. Questions? No? Eric?
Okay, since this is a prototype for OpenFOAM, I wonder how hard would it be to try to generate CSR matrices within YoctoFOAM?
That's the thing. We already have all the infrastructure in place because Mirko Valentini already implemented the CSR format inside YoctoFOAM. So, I mean, we did not do the porting yet. So, but it would take really little time to do those tests because it's almost already there. Yeah, we can also do assembly in CSR.
Okay, next presentation is by GPU acceleration of CFD simulation OpenFOAM by the group of Federico Pescaia from DAIR, and the presenter is Federico Ghioldi. Please, Federico.
Thank you very much. So yes, as Ivan said, I'm talking about GPU acceleration of CFD simulations in OpenFOAM. Thank you very much for being here. So I want to start by thanking, of course, all the people who helped us and were also collaborators with us. So I see a lot of people here. So the group of HexaFOAM and the OpenCFD, of course, and the HPC technical committee, which were very helpful in providing us some suggestions and observations throughout the work. That has been quite long, as you will see later. I want to start by saying that this is taken from the NVIDIA website. You can see that there are people who are using different kind of hardwares, let's say, to develop their simulations. And since our goal is to accelerate the use of, accelerate the simulations in CFD by means of GPUs, it is important to understand those numbers and to have these information. But it's also important to understand that whenever we are dealing with a different hardware, we also have to, let's say, manipulate or modify a bit the algorithms that we have in our hands, because this improves, of course, the possibility to use hardwares which are designed in a much different way with respect to the common CPUs that we use every single day, pretty much. So, as I was saying before, you see that the work that we have been doing is quite long, let's say, and we have been doing it for quite a few years. So you see some, let's say, some evolutions throughout the years, but the most important one to me is 0.7, not only because it's the last one, but also because it's the GPU pilot project, which is soon be released by OpenCFD, so it will be public, and it will contain let's say, the topics that I'm going to discuss in this presentation. So sorry for making it so long, but I'm going to quickly discuss about these three topics in particular, focusing a little bit more on the second and the third, because the first one has been covered so many times throughout this workshop. So yeah, the first one is related to the GPU computation for fast, large-scale CFD simulations, but mainly related to especially external aerodynamics, usually. For the second part, instead, is the work related to the acceleration of reactive flow simulations by, let's say, porting to the GPU the ODE solution. And I will focus a little bit more on that. And then I will move to the thermal radiation problems, because, of course, that is related to something which is like a specific application of OpenFOAM, but it's something that the industries usually require whenever they're dealing with thermal radiation, which is the acceleration of the pre-processing and the calculation of the view factors, which is extremely important for them. So let's start from the first one. So I will present a library pretty much, which is AMGX4FOAM, but is like the combination of two libraries that you have already seen, but is PETC4FOAM and FOAM2CSR that have the acknowledgements that we have to make are to OpenCFD, of course, and NVIDIA guys. The idea is, of course, to accelerate the solution of external aerodynamics, so the fluid dynamic equations, by means of AMGX in this case. We need to provide some sort of combination between OpenFOAM and AMGX. And this was done by, of course, transforming, first of all, the matrices into the CSR format so that you can handle the problem on AMGX. And then, of course, you need to have an optimized data transfer and then exploit the libraries provided by NVIDIA in order to accelerate this kind of operations. Now, the tests that we have been done were related to incompressible CFD simulations, as typically is the case for, let's say, external aerodynamics in this particular cases. We started from steady state simulations, but we're moving towards unsteady simulations because as other presenters have said, the first thing that we wanted to accelerate was the calculation of the P equation. And whenever you have unsteady simulations, it's, of course, the number of times that you solve the P equation increases. And so, of course, that produces a further improvement if you try to accelerate unsteady simulation in this sense. So I will not stay too much on the governing equations because this is something that everybody knows. So I will just save you this time. And this is something that I've pretty much already said. So you need to have PETC4FOAM in order to extend the solver portfolio, but also to, let's say, combine the possibility to have a FOAM2CSR, so a transformation of the LDU matrix into the CSR format. And thanks to these two libraries that are combined into the AMGX4FOAM, you can indeed accelerate the simulation by means of AMGX. The work that we are currently doing is to try to make these two libraries even more lightweight so that we can remove, if possible, or reduce the amount of operations which are currently done in order to try to further reduce the possible bottlenecks which are present inside of this kind of operation. And I want to, of course, provide to you some references if you are interested in the topic. So the requirements are pretty much simple. You just need to have CPU cores and an NVIDIA GPU card because we are, let's say, exploiting AMGX, which is powered by NVIDIA. And currently, this is done with the AZ version of OpenFOAM. And of course, then you need the CUDA toolkit and AMGX. And in order to have everything available, you need to have AMGX4FOAM. The thing is that in AMGX4FOAM, especially if you look at the documentation, there is all the necessary steps, and it's pretty much automatic. It will just allow you to download and use CUDA, the CUDA toolkit, and AMGX. So it's just a library that you have to download, and then you have to look at the documentation. It will tell you exactly how you can, let's say, first of all, install all the things that you need, and then how to set up a case. The setup of the case is similar to the setups that you have seen for PETC, the setups that you have seen for Ginkgo. So it's pretty much similar. You just need to add one other file at the current state, which is in the system folder, a file which contains the options for AMGX. It's something that we're planning to reduce, okay, and remove, so that it makes it even simpler for the end users to use AMGX out of the box. And the AMGX solvers are, I mean, you have plenty of available options inside of AMGX, so you can pretty much replace, let's say, the options that you have nowadays in OpenFOAM. The known differences, but they are currently being worked on, is the fact that using AMGX, there is a different way to calculate the residuals. And so this implies that if you take like your simulation and you apply the same final residual, let's say, you will get, of course, a different behavior, because as you can see, you have a different behavior I mean, the initial residuals are pretty much the same, but if you look at the final residual in red, you will see that there is a slightly different behavior. So this is a known, let's say, difference, and the guys from AMGX are already working on it in order to update this kind of procedure. So the test cases that we have developed, well, as I said, we started from steady state problems, and then we moved to unsteady problems. They are contained into the HPC folder, okay, from the HPC committee. You can find them, you can play with them, and provided that you install AMGX for foam, you can play with AMGX and not only the cases. The newest update is the fact that we are aiming, as I was saying, to unsteady problems, and so you have a tutorial case, because it's not mainly related to physics, but it's mainly related to possibility to accelerate the problem. So we are just dealing with tutorials at the moment. You see here the results, and you see here that the GPU is able to correctly predict the behavior of the fluid dynamics. So it produces results, and we have investigated qualitatively and quantitatively, and you can see that the results are pretty much in line with those provided by OpenFOAM. So they are in very good agreement. In terms of speed up, we started with, let's say, small simulations, because as I showed at the very beginning, there are a lot of people who are using few cores, okay? And so we tried to use few cores in order to understand whether we have advantages or not. And at the moment, if you if you compare solver against the solver, and so if you compare PCG against PCG from AMGX, or if you compare GAMG versus GAMG in AMGX, there is some slight improvement already at few number of cores, but you need to go to much larger meshes and much more computational, let's say, problems. So much more expensive problems to see a proper let's say, result, a proper speed up as the one that was shown before. But at higher numbers, we confirm what has been already said by other presenters, and we see that there is a certain speed up, which is in the order up to 2 per. Pretty much. So, two per. Yeah. 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 Yeah, but again, we are talking about smaller meshes and few number of cores. So in this case, this is just the fact that for few number of cores, for few, number of cells, at the moment in the current state, because of the way GAMG is written in OpenFOAM, because of the way the efficiency that it has, the much larger improvement is found in again PCG against PCG. Yeah. Yeah. These are steady problems, and so this means that pretty much these are iterations for a steady problem. Okay, so let me move to something that let's say in our group we developed, and is related to the GPU acceleration of chemically reactive flow problems. We're not dealing with a library here in terms of like provided by AMGX or other groups, but we just developed an acceleration of the calculation of the ODE integrations. So in order to accelerate the calculation of the ODE integration, we designed that structure that you see right there. in particular, this structure is able to provide to you a double parallelization between cores and threads available in the GPU. We're able to decompose our problem over multiple levels and try to obtain a certain speed up. Again, whenever we are dealing with GPU operations, we need to redesign or co-design all the integrators, which is already available in OpenFOAM, in order to exploit this double parallelization and obtain a certain speed up. And suit, of course, heterogeneous architectures. Again, I will not stress too much the equations, but the thing that we are trying to compute is this term here. So the result, let's say the chemical source term related to the calculation of the ODEs, which is then updated by means of a combustion model and produces, of course, this term. So we are trying to obtain a speed up in the calculation of this because we have investigated and we have found that was also said by another presenter, that of course this produces a huge increase in terms of the computational time. And so we wanted to accelerate it. In order to do that, we need to combine the CPU with the GPU by means of an extern C function, and we need to transfer certain data, not all the data, but certain necessary data from the CPU to the GPU, so from the memory of the CPU to the memory of the GPU. And once we are there, we need to, let's say, exploit the capabilities of the GPUs and the architecture that the GPU provides. So, of course, the GPU has a certain hierarchy. It's composed by blocks and threads, and we need to decompose our problem in such a way that we optimize the use of the GPU. And so we designed this, let's say, double parallelization, which considers every single cell in the computational domain as a CUDA block, and every single species contained inside of the cell as a CUDA thread. So this implies a double parallelization, as you see there. And this also requires a certain manipulation of the data in order to be suited for this kind of operation and the use of the different kind of chunks of memory which are provided by the GPU cards. Not only the, let's say, dynamic memory, which is usually used in these kind of applications, but also the constant memory to try to avoid to pass multiple times data which are not updated throughout the simulation. And it is extremely important the use of shared memory, because at some point the species need to communicate one another to share information and, of course, provide a certain update, so obtain a certain evolution. And so the shared memory, being case dependent, needs to be dynamically allocated before the execution of the simulation. And this is, of course, done automatically in our code. So this is the procedure and the workflow. So basically what you have is the calculation of the fluid dynamic equations as you typically have in OpenFOAM. But at some point, you need the chemical source terms in order to update the transport diffusion equations for the chemical species and to update, of course, the terms inside of the energy equation. So instead of computing that or the system by means of OpenFOAM, you just pass the information that you need to the GPU, you compute the chemical source term, and then you retrieve only that information. And once you have retrieved the information, you set it back to OpenFOAM, and you can of course proceed on with your calculation. I've said pretty much everything here. The only thing which is extremely important is the fact that we started from explicit ODE integration because the GPU likes explicit operations. And so we started from this, but the way the code is designed, it allows the possibility to have other ODE integrators. And so you can decide to implement other ODE integrators, and we're planning also to try to implement some others so that we can enlarge the portfolio of available ODE integrators that you have in this let's say, library that we are providing. So the test cases that we studied were at the beginning, like very simple cases like single cell batch reactors. The reason is we don't have fluid dynamics, so we're only investigating the behavior of chemistry, and we can validate the correctness of the simulation. Then we moved, of course, to multi-cell cases, and then finally we moved to more complex cases. For example, being from the aerospace department, we investigated the scramjet configuration, which is 3D and quite complex in terms of combination of combustion and turbulence and so on. So as you can see, the explicit CPU GPU ODE integrator is able to provide correct results. Is pretty much in line, has good agreement with OpenFOAM. We tested, of course, different fuels. We tested different thermochemical conditions. We moved on to multi-cell cases, and then that we moved to more complex simulations. So of course you're interested in the speed up, and of course this is what comes out and you're mainly interested into, but this is what I wanted to focus more. The thing is that whenever you are accelerating or you're trying to accelerate a problem by means of the GPU, you don't only have to compare the time which is taken for the GPU to complete that task, but you also need to take into account all the additional times that you are introducing because you are dealing with an heterogeneous architecture. So the point is that you are not only taking into account the fact that you have to allocate the memory, copy the data, perform the actual operation on the GPU, and then retrieve the information that you need, but there is also sometimes the need to remanipulate the data before you transfer it to the GPU. And the improvement, you have it as long as the overall time taken to perform this task onto the GPU is lower than the time taken to perform the same task on the CPU. And so we started from simple cases, and we already saw a certain speed up. And then we moved to more complex cases. And because of the double parallelization and because of the fact that we have this subdivision and we're solving cells in parallel and species in parallel, well, this is done serially in OpenFOAM, the speed up can increase a lot. And we reached something that was close to 10 per. Finally, sorry for being so long, but let's move to thermal radiation, which is another problem that we had to tackle, and you will understand why at the very end. So the problem of thermal radiation is mainly related to the calculation of the view factors. This pre-processing results to be quite tedious and long for some industries, and especially we're aiming at speeding up all the simulations, but then we find at some point that the pre-processing, in some cases, it might take as long as the development of the simulation. So we were asked to try to find a way to accelerate the calculation of the view factors, and this is an application in OpenFOAM, as you know, and we evaluated the function, the application, and we said, okay, there are two steps, the two parts that we can accelerate. The first one, as everybody can think, is the ray tracing. The second part is the actual calculation of the view factors. So the way the application works is the ray tracing is done in order to understand which face sees the other. And then once you know this information, you need to actually compute the elementary view factor. So the elementary contribution of that, view factor on the visible face. Okay. So when we sped up the ray tracing, we found at some point that the calculation of the view factors, because of 4 nested for loops, was becoming the bottleneck. And so we had to sped up that as well. So again, these are just the governing equations, but I will not stay too much on this. I want to explain to you that the way OpenFOAM works, you have 2 different kind of grouping of faces. So every single elementary face that you have in your boundary is a fine face for the view factors calculation. While instead, for the boundary, whenever there are multiple faces which have the same normal direction, at that point, you see that they are coalesced, let's say, into a coarse face. Now, in terms of visibility, OpenFOAM works considering the visible face against the visible face in terms of coarse faces. But whenever it's time to compute the view factors, you need to calculate each elementary view factor. And so, of course, this becomes quite expensive in terms of calculations. So the thing that we did was to accelerate, as I said, the ray tracing by, re-implementing the Muller-Trumbo algorithm without moving the entire OAK3 space discretization onto the GPU. That would have been not needed and very complex. And then what we did was to accelerate the calculation of the view factors. And thanks to the use of the atomic reduction, you can avoid the presence of 4 nested loops that are indeed present in OpenFOAM. So just to move on to explain the workflow. Okay, so in the previous case, so for the ODE integration, we use the fat thread approach. I don't know if you're familiar with that, but it simply means, okay, I'm finishing. But it just implies that you have blocks and then threads, and then you have shared memory. And so every single cell in that case was treated as a block. In this case, we just consider every single phase as a thread inside of the GPU. So we have a thin thread approach, which is very, very good for the calculation of the ray tracing, is less good for the calculation of the view factors, and that's why we needed to create another kernel by using a different approach for the calculation of the actual calculation of the view factors. So the way the workflow works is you collect the data which is necessary for the ray tracing, you perform the ray tracing calculation onto the GPU, you obtain the visible vector of the faces, but you don't have to retrieve it back. There is no need. Nobody needs these vector onto the CPU, and so you just keep it on the GPU. You just evaluate whether the problem is 3D or 2D, because of course there is a difference in the calculation of the view factors, and you just enter in one of the two options. You perform the kernel call 2, so you perform the calculation of the view factors by using something which is already resident on the GPU, and then you retrieve the final information, which is the value of the view factors, and you move it back to the CPU in order to be printed or be saved onto the mesh. We tested some cases. We started from very simple cases because they were, of course, cases that had analytical solutions. We are progressively moving towards more complex cases like the one of the car that you have seen in a previous slide. I just wanted to show you that in terms of accuracy, in green you have the GPU accuracy, which is very, very high. It's in line with the results of OpenFOAM. And here you see what I was talking about before, and then I will conclude, is the fact that this is the calculation of the ray tracing. Whenever you are, let's say, introducing GPU calculations, this one is not optimized, of course, then you have a parallel version of the solver. But if you take the calculation and you move it to the GPU, one thing that you have is an additional, let's say, increment of an additional time, let's say, which is the host to device data copy forward and backward. And once we parallelized the calculation, we found a huge speed up. So you see here some results in terms of performance. I think you might be interested in these figures even more, which is in terms of like the calculation of the ray tracing and the view factors, just a single operation, you can get to up to 10, 20 per speed up on the cases that we tested. Unfortunately, the issue that we have is that the data needs to be managed from OpenFOAM in order to be moved to the GPU. So in some cases, imagine that we have like the 4 nested loops which are completely removed because we're using the GPU, but at the same time, we need to have 2 for loops on the CPU because we need to, let's say, combine the data in such a way that it's suited for GPU calculation. So in that sense, we aim to reduce or try to find a way to overcome that as well. So here instead, you see the performance of the overall run. And you can see that, I mean, this is the performance considering 1 core against 1 GPU. Some industries do exactly like that. But we also wanted to try to see what happens if we increase the number of cores, and we see what happens in terms of the CPU against the single GPU. And you can see that for the cases that we tested, we still have a good result compared even to 16, 32 cores, CPU cores. So finally, and then I conclude, sorry for taking so much time, I showed you like the work that we, in some cases with collaboration with very precious collaborators, we have developed. So YoctoFOAM, reactive flow simulations by means of the GPU or the integrator, and the thermal radiation, so the calculation of the view factors. I showed you pretty much these let's say, ideas and these developments, because the next step would be to try to combine all the methods that you have seen here and to see what are the performances in developing a simulation which is much more complex, which takes into account all these procedures. Thank you very much. I think you might have plenty of questions. I'm here to try to answer.
Everyone, of course, everyone is talking about moving data forward and back on for GPU, CPU. You have shown that you have to take into account this. This is something that is a bottleneck, simply by the design. I'm very curious to see what is going with the unified memory GPUs from Hopper, from AMD, and from Intel. Is now 1 year. That is.
Also because of the presentation of Stan.
Yeah, probably.
Show that
The Hopper is together, the ARM with Yeah, I'm I'm eager to see when we are ready, honestly.